All right, guys, we're gonna continue with section 14.5. We're gonna finish it. Chain rule for z equal f x y, where y equal t uv. Yeah. Yeah. So x and y, they are function of u and v. But f, right? X, y. X is the function of u and v. Y is the function of u and v. So when we go down the tree diagram, we're going to be using partial derivative. And when we continue down, it's going to be partial derivative. Partial derivative of f with respect to u. Right? It cannot be with respect to x because the function f, even though it is in terms of x and y, x is in terms of u and v. So you got to take the partial derivative with respect to either u or v. Right? So there's two of them. The partial derivative with respect to u is going to be well, you go down to the branch that has the u, right? Partial with respect to x, partial x with respect to u, partial with respect to y, partial with respect to u. Okay, so we are finished, right? There's only one. You got to do the other one because the f in the end is the function in terms of u and v. So you got to do another one. And pretty much do the same thing. You just have to change u into v. Just follow this thing. We only want to do partial s with respect to x, right? They're going to be this one. Partial s with respect to u and partial u with respect to x. Partial s with respect to v and partial v with respect to x. That is it. Right? So partial s with respect to x is going to be a partial s with respect to u, partial u with respect to x, partial s with respect to v, partial with v with respect to x. Okay, so this is what it looked like. Work it out. Take the partial derivative with respect to u. It's going to be you're going to have to use this one. Right? So that's going to be 2u over root of u squared plus v. Partial u with respect to x. Well, you don't have any x there, so it's going to be 0. If you have any question, just let me know. Right? There's no x there because u is equal to y, so it's going to be 0. Partial s with respect to v, so it's going to be 2v over root of u squared. Ooh, it's too small here. Plus v squared. And then partial v with respect to x is going to be -2. Right? So what do we have here? We have a -4v over root of u squared plus v squared. Oh, we haven't done yet though, because in the end, the function is in terms of x and y. So you have to do the substitution here. Sub it in. -4 v is negative 2x over square root u square, so 2y square. Actually, let me just do the substitution here, and we're gonna be looking at this thing in a bit. Okay, we have this one. Next, try to simplify it. Oh yeah, 1/2. Yeah, I forgot 1/2 here. Yeah. 1/2. Yeah, because this is the half. Yeah, you have the 1/2 right there. That's 1/2. So it's gonna be -2. It's just -2 here. Okay. Yeah. So we have a -4x over. This one is going to be a 2 root of. Oh man, this look like a zero. 2y and then -2x. Come on. Okay, now it looks better. Y square plus x square. So in the end, it's going to be a 2x over root of. I usually do x square plus y square. Yeah. Okay. Let's do one, and then I'm gonna move on to a differential equation, show you why this thing is useful. Okay, here come one. Let w equal x y plus yz plus zx, where x equal r cosine theta, y equal r sine theta, z equal r theta. Phi partial w with respect to r at 2 pi over 2. Right? This is r. This is theta. I'm going to do the sub first there, because we are taking partial derivative with respect to r. And we are r cosine theta, r sine theta plus r sine theta, r theta, r theta, r cosine theta, r square sine theta, cosine theta, r square theta, sine theta, r square theta, cosine theta. Now we can do a partial with respect to r. 2r sine theta, cosine theta. Yeah, if 2r theta sine theta, 2r theta, cosine theta. Okay, now I'm going to do the substitution in here. 2 pi over 2, 2 times 2, sine pi over 2, cosine pi over 2, 2 times 2, pi over 2, sine pi over 2, 2 times 2, pi over 2, cosine pi over 2. Okay. Cosine pi over 2 is 0. It's going to be a so it's going to be 0 here plus 2 pi sine pi over 2 is 1, and then that is 0. So it's 2 pi. Yay! 1. I just use the tree diagram here and grab this thing, right? F is the function in terms of x and y. So we know x is the function in terms of just x, y is the function in terms of x. This is the layer right here. Everybody see this? So when you do the first layer, it's going to be a fx that I'm using the shortcut because this is so small, fy. And then this is the dx over dx, dy over dx. But then we know dx over dx just 1, right? So in order to solve for dy over dx, right, we're gonna have to look at this equation, and then we're gonna take the derivative with respect to x on both sides. Take the derivative with respect to x, right? Okay. When we take the derivative with respect to x, on this side is going to be the chain rule. And the chain rule is right there. It's the fx times 1 plus fy times dy over dx. Right? And it is 0. It's right there. Right? So it means dy over dx is gonna be negative fx over fy. So this is the formula. I'm gonna do a quick example to show you the power of this formula. Use the formula. To do implicit differentiation of to differentiate the equation implicitly. The equation below implicitly. Here comes the equation. x3 plus y3 equals xy. Can do this one real quick here. And this one is sit y plus sit x y prime. Okay, let me see if we get the same thing here. I'm gonna move everything. So it's gonna be 3y squared minus 6x y prime 6y minus 3x squared. Oh, I see it's the same thing here. So y prime is 6y minus 3x squared over 3y squared minus 6x, and simplify this thing is going to be well, it's the same thing, 2y minus x squared over y squared minus 2x. Now, I think the partial derivative is a little faster.